Welcome to Comparative Anatomy of Vertebrates. Imagine being trapped in a crowded, stuffy room where the air conditioning suddenly breaks down. You would naturally want to step outside for a breath of fresh air. Fishes living in stagnant, muddy, or drying tropical ponds face a very similar, deadly problem when their water runs out of dissolved oxygen. Today, we are going to explore how some incredible fishes evolved backup breathing systems to survive these extreme conditions. Now that we understand the basic problem, let us look at the environments that drive this adaptation. In many tropical regions, ponds and swamps frequently become stagnant, muddy, or even dry up completely during certain seasons. When this happens, the water becomes severely hypoxic, which simply means it has dangerously low levels of dissolved oxygen. Traditional gills are wonderfully efficient in healthy water, but they are completely inadequate when the oxygen simply is not there. Without a backup plan, ordinary fishes would quickly suffocate. This intense environmental stress is the driving force behind one of nature's most fascinating survival strategies. To survive these harsh conditions, nature provided a solution. Accessory respiratory organs are specialized anatomical structures found primarily in certain teleost fishes. Unlike traditional gills, which are strictly designed to pull dissolved oxygen out of water, these unique organs act as a backup system to extract atmospheric oxygen directly from the air. Fishes like the climbing perch or the walking catfish use these organs to supplement their gills or sometimes replace them entirely when the water quality drops. By gulping air from the surface, these fishes can survive in severely hypoxic waters and can even remain alive completely out of water for extended periods. Knowing what these organs do, we must ask where they come from. Evolution rarely builds from scratch. Instead, it modifies what is already there. These accessory organs arise as structural modifications of various existing body parts, such as the pharynx, the branchial chamber, the stomach, the intestine, or even the swim bladder. For these modified structures to function effectively as lungs, they must be highly vascularized. This means they are packed with a dense, rich network of blood vessels. This extensive blood supply is absolutely critical, as it maximizes the absorption of atmospheric oxygen directly into the fish's bloodstream. This anatomical shift leads us to a massive milestone in the history of life. The evolutionary importance of accessory respiratory organs cannot be overstated. They represent a crucial transitional step in vertebrate history, bridging the gap from purely aquatic life to terrestrial life. In real-world ecosystems, these organs allow fishes to inhabit marginal, harsh environments, like agricultural rice paddies, where ordinary fish would quickly perish. This incredible adaptation gives them a massive survival advantage. It allows them to escape aquatic predators and even exploit new food sources by temporarily moving across damp land. Without this evolutionary leap, the path toward land-dwelling amphibians might never have occurred. To truly understand how these accessory organs work, we must look at the underlying physics. The efficiency of any respiratory organ is governed by Fick's law of diffusion. This fundamental law dictates how quickly oxygen molecules move from the air into the bloodstream. Let us break down the formula. R is the total rate of gas diffusion. D is the diffusion coefficient, a constant for the specific tissue. A is the total surface area available. Delta P is the difference in oxygen pressure between the air and the blood. Finally, D is the thickness of the membrane. To increase oxygen uptake, the fish must maximize surface area and pressure difference while minimizing membrane thickness. This is exactly why accessory organs are highly folded and extremely thin. Before we move on, let us see this with a concrete example. We will calculate the oxygen diffusion rate for a climbing perch using its labyrinth organ. We are given a highly folded surface area of 0.05 square meters, a membrane thickness of 0.0001 meters, a pressure difference of 10 kilopascals, and a diffusion constant of 2 times 10 to the negative fifth. We substitute these known values directly into Fick's law. Multiplying the numerator gives us the total driving force for diffusion, which is 1 times 10 to the negative fifth. Dividing by the tiny membrane thickness drastically amplifies the result. The final rate is 0.1 units per second, proving mathematically why this highly folded organ is so effective. Now that we have used Fick's law, let us understand how a fish chooses its breathing strategy. Why would a fish use its accessory organ instead of its gills in a stagnant pond? We can determine this by comparing the diffusion rates in both environments. Because the physical organ remains the same, we can simplify our comparison into a simple ratio. The ratio of the diffusion rate in air to the diffusion rate in water is equal to the partial pressure difference in air divided by the partial pressure difference in water. If the pressure difference in the air is higher, the ratio will be greater than 1, indicating a clear biological advantage to surfacing and gulping atmospheric air. Let us apply this ratio formula to a real scenario. In muddy, stagnant water, the oxygen pressure difference drops dangerously low to just 2 kilopascals. However, if the fish gulps air from the surface, the atmospheric pressure difference is a much higher 15 kilopascals. We want to find out how much faster oxygen diffuses from the air compared to the water. We set up the ratio by placing the atmospheric pressure difference of 15 in the numerator and the aquatic pressure difference of 2 in the denominator. Dividing these gives us 7.5. This means oxygen diffuses into the fish's blood 7.5 times faster when it gulps air. This massive, life-saving boost perfectly explains why these fishes constantly surface in poor conditions. So, we have proven that air breathing provides a 7.5 times advantage. This brings us to an important question. Where did that simple ratio formula come from? Let us derive it directly from Fick's law. First, we write out the full Fick's law equation for the rate of diffusion in air. Next, we write the exact same equation for the rate of diffusion in water. To find the relative advantage, we set up a ratio, dividing the air rate by the water rate. We then substitute the full Fick's law expressions into the numerator and the denominator. This sets the stage for us to simplify the complex physics into a highly practical biological rule. Continuing from our setup, let us simplify the mathematics. When we divide by a fraction, it is the same as multiplying by its reciprocal. Because we are looking at the exact same fish using the exact same organ, the diffusion constant, the surface area, and the membrane thickness are identical in both scenarios. Therefore, all of these structural variables perfectly cancel each other out. This leaves us with a beautiful, simplified result. Because Fick's law is linear with respect to pressure, the ratio of the final diffusion rates is exactly equal to the ratio of the partial pressures. This proves why our simple calculation earlier was completely accurate. Now that we understand the physics and the math, let us visualize the actual biology. Here we see a detailed anatomical cross-section of a fish head, specifically highlighting the labyrinth organ. Notice the highly folded, rosette-like structure located in the suprabranchial chamber, just above the standard gills. This extreme folding is exactly what maximizes the surface area we discussed in Fick's law. You can trace the red arrow at the mouth, showing atmospheric air intake, which travels up to this vascularized organ. The red and blue arrows around the labyrinth organ represent the rich network of oxygenated and deoxygenated blood flow. Finally, the depleted air exits near the operculum. This diagram perfectly illustrates the physical adaptation required to breathe atmospheric air. We have covered a tremendous amount of ground today, so let us review the most important ideas. First, accessory respiratory organs are brilliant evolutionary workarounds that allow fishes to survive in severely oxygen-poor environments. Second, by modifying existing anatomical structures into highly vascularized surfaces, these animals conquer the limitations of aquatic gills. Third, as we proved using Fick's law, maximizing surface area and exploiting the high pressure of atmospheric oxygen provides a massive life-saving advantage. Ultimately, these incredible organs highlight the extreme adaptability of vertebrates, and they beautifully foreshadow the evolutionary transition to terrestrial lungs. You now have a complete understanding of accessory respiratory organs.